The network designer has numerous options on how to connect the incomers, bus bars and feeders together to create a fully functioning substation. This section introduces some of the main configurations that we use to connect these three elements together. By the end of this section, you should know the main network configurations that we use and understand the benefits and disadvantages of each. The aims of the course today are: look at the differences between switching stations and substations. Introduce the basic elements that make up a substation or switching station. Look at the most common configurations for substations and switching stations. Most electrical networks consist of three main parts. Firstly, we have the generation. This is where the electricity is produced in a power station, either gas, oil, coal or nuclear. The typical output voltage from the power station is 12,000 volts. We then have the transmission network, where the 12,000 volts produced by the power station is stepped up to a higher voltage using a transformer. We step up the voltage to minimize the losses on the network and increase the amount of power that can flow through it. The power is then distributed over the transmission network using overhead lines and cables. The typical transmission voltages are 115 kV, 230 kV or 400 kV. Finally, we have the distribution network. We now step down the voltage using a transformer so that it can be used by industrial and residential customers. We normally transport the power through the distribution network using cables. The normal distribution voltages are 415 volts, 11 kV or 33 kV. There are two main types of stations on the transmission network: switching stations and substations. A switching station has no transformers and only operates at a single voltage level. It is used to switch electrical energy around the transmission network, connecting the power stations to the cities and load centres. A substation takes the energy from the transmission network and steps it down to a lower voltage level using a transformer. Each transmission substation consists of the following key elements. Incomers. These feed power into the substation. Bus bars. These connect the different circuits together. Bus couplers and bus sections. These allow different bus bars to be connected together. And finally, feeders. These take power out of the substation and can either be plain feeders or transformer feeders. There are many possible ways to connect the incomers, bus bars and feeders together. Here are the most common. The first type is a transformer feeder. This is a very simple circuit with a high voltage incomer, a transformer to step the voltage down, and a low voltage feeder. These are used widely in networks to step down the voltage to a lower level. The high voltage and low voltage connections to the transformer can either be via a cable or an open terminal substation. Let's see how this circuit works in practice. We can see that the high voltage incomer is now live. We close the isolator on the incomer before closing the incomer circuit breaker. This now energizes the transformer. Let's now close the low voltage circuit breaker. Again, we close the isolator before closing the circuit breaker. Power is now flowing from the high voltage incomer through the transformer and through the low voltage feeder. Next, we have a single busbar substation. This is a simple configuration to connect a single incomer to several feeders. Let's see how this configuration works. Firstly, we close the isolator on the incomer before closing the incomer circuit breaker. The busbar is now energized. Let's now energize one of the feeders. Again, we close the isolator before closing the feeder circuit breaker. Power is now flowing from the high voltage incomer and through the low voltage feeder. The main issue with this type of configuration is that if the main incomer supply is lost, or a fault occurs on the common busbars, or it needs to be maintained, all feeders will lose their supplies. One solution to this is a split busbar substation. To give us more security, we add another incomer as an alternative source of supply. We also add a bus section circuit breaker, so that if one busbar is out of service, we can still supply some of the feeders. Let's now close the circuit breakers. The normal configuration, when both incomers are available, is for each incomer to feed its own busbar, with the bus section breaker open. Let's now see what happens if we lose one of the incomers. Firstly, we close the bus section isolators before closing the bus section circuit breaker. In practice, we normally leave the busbar isolators permanently closed, so that when an incomer fails, we can quickly close the bus section circuit breaker and energize the dead busbar. This arrangement is also called a 2 out of 3 system, but the normal operation is to have 2 of the circuit breakers closed at any one time. Another popular configuration is a double busbar station. This configuration provides multiple options for connecting the incomers and feeders together. As you can see in this arrangement, we have 4 busbars. Each of the incomers and feeders can be connected to one of 2 busbars using the busbar isolators. We can also add bus coupler circuit breakers to connect the upper and lower busbars together. Let's now close the circuit breakers. The normal configuration is for each incomer to feed 2 busbars. As we can see, incomer 1 is feeding busbars 1 and 2, and incomer 2 is feeding busbars 3 and 4. One feature of this arrangement is that we can change which busbar a feeder is connected to without disconnecting the load. This is done using what's called an on-load changeover sequence. Let's now see how we achieve this. Firstly, we close one of the bus couplers to connect the 2 busbars together. The bus coupler has an inbuilt synchronizing relay to make sure that the parameters on each busbar are the same. Once the bus coupler is closed, we can close the second busbar isolator on each of the feeders. Once this is done, we can open the original busbar isolator, and we've now changed over which feeders the busbars are connected to. We then open the bus coupler circuit breaker again, splitting the busbars. Additional busbars are added to give the network operator more options to connect the incomers and feeders together. Having one busbar per incomer is a common configuration. To provide even more flexibility, the busbars are connected together using bus sections and bus couplers. Ideally, it should be possible to connect any feeder to any incomer to balance the loads on the network and allow flexibility when a fault occurs or a circuit needs to be taken out of service for maintenance. Another popular arrangement for switching stations is a breaker and a half arrangement, sometimes called a diameter. In this arrangement, we have 2 common busbars connected together with bays that have 3 circuit breakers each. The bays can have an incomer and feeder, or alternatively 2 feeders. This configuration is quite common for transmission level switching stations, where power is simply flowing in and out of the station, i.e. no transformers. We can connect any incomer to any feeder via any busbar, so the arrangement is very flexible. Let's now close the circuit breakers. In this arrangement, power is flowing from incomer 1 onto busbar 1 and onto the feeders connected to that busbar. Incomer 2 is connected to busbar 2. Let's see what happens if we lose the supply to incomer 1. The arrangement is now automatically reconfigured, with incomer 2 now feeding both busbars and all of the loads connected to them. The breaker-and-a-half arrangement is popular around the world, as it gives a cost-efficient way of providing a very flexible design, which is easy to expand should the system demands increase. The number of bays that can be tied together is virtually unlimited, and I have worked on high-voltage transmission substations that have had over 25 diameter bays. The layout of a diameter substation will also make up less physical space when compared with an equivalent double busbar substation, which can also save substantial amounts of money for purchasing the land required. Finally, we have the mesh station. This is another common switching station configuration and is similar to the diameter arrangement in its flexibility. Each of the corners is defined as a mesh corner. In this case, we have mesh corners 1, 2, 3, and 4. To connect the mesh corners together, we have the mesh corner circuit breakers. We have circuit breakers 1-2, 1-3, 2-4, and finally 3-4. The mesh corner isolators are used to redirect the power flow. These can only be operated offline, so we have to control the flow of power into the substation using the remote end breakers. We therefore rely heavily on a communication link to the remote ends. A typical configuration is for each incomer to feed its own mesh corner. Let's now see what happens if we lose the supply to an incomer. As we can see, the system is automatically reconfigured using the circuit breakers and isolators. Because of the complexity involved, the control circuits and protection requirements for this type of station can be quite complex and difficult to maintain. This is why this arrangement is not as popular as it used to be. Let's summarize what we've learned today. Most air-insulated substations contain incomers, busbars, and feeders. We use bus section circuit breakers and bus coupler circuit breakers to connect the busbars together. There are many different substation configurations. These are chosen depending on the number of incomers and feeders and the flexibility required from the station. Congratulations for completing this section. You should now have a good understanding of the different substation configurations we use on the network, and realize why the network designer has chosen that particular configuration for the air-insulated substation. I've attached some questions on today's section to test your knowledge.